let's talk about okay, so anyone remembers why we had to look for another converter other than flyback converter? Anyone remembers that? Yeah, because flyback converter is like buck boost converter. There was one question which somebody asked, which we didn't answer at that point, which was that why am I saying that buck boost converter will have more ripple as compared to a simple buck converter, for example, right, at the output side. So that part I didn't answer that time. Maybe I'll quickly answer, because that is also in a way the basis why flyback converter is not good enough, right, and you have to look for other converters. So before we go to this point, let's have a quick look at it. I will not do the detailed derivation, you can do it if you want, but I'll just give you an idea. So if you have this converter, right, this is your buck boost versus this is your buck. Of course the polarities are different, right? If you see the current which is coming to the combination of capacitor and resistor, right, this current, let me call it I1 in buck boost and I2 in case of a buck. So I1 waveform would be, when the switch is on, I1 would be 0 and then it will be like this. On the other hand, I2 waveform would be something like this, right. So by keeping a larger inductance value in buck converter, you can ensure that I2 has a smaller ripple, which you cannot do in buck boost. Buck boost, even if you kept the L value infinite, still the current going from here would be like a square wave, right. This slope will go away, this will become flatter, but you still would look like a square wave. So you have to have a large value of capacitance at the output so as to absorb this ripple current. And therefore, if you see qualitatively, if you want to work with same capacitance values, same inductance values, this would have smaller output voltage ripple as compared to buck boost. Is that okay? So therefore, we always say that if you just have to do buck, just do buck, don't use buck boost, right? Is that doubt okay? Yeah, in case of boost, yes, the same phenomena will happen. So on the output side, your ripple would still be substantial, but boost helps in case of input ripple. So, but buck boost doesn't help either way, because inductor is in the middle, right? So either input current, output current, both will have large ripple. In boost, at least the input ripple is small, which makes sense a lot of times. For example, if your source is solar photovoltaics, right, solar panel, then you don't want to draw large ripple from those panels. It creates certain challenges which we cannot discuss now, but you cannot do that, large ripple from a source also. So therefore, in those cases, you can use a boost converter, right, so that you have an inductor on the input side. Now, since we have talked about it and since this question has come, there are certain converters, there is a family of converters where you have inductor both at the input side as well as at the output side, right, and therefore both input ripple and output ripple are small. There are those kind of converters also, a bit more complicated, but they also exist, right, DC-DC. But we are not going to sort of go into those topologies, but you get an essence of why we always say that this has a larger output voltage ripple as compared to a buck converter.
In buck boost, we are concerned with I1 ripple, right, not with the inductor ripple.
So finally, we are worried about the output voltage ripple, because that is what gets applied to your load, and we are worried about, of course, the input voltage ripple, because that is what gets applied to the source, if your source is sensitive. Whatever happens inside converter is still fine, it happens within a box, right, but you are worried about the output and the input side, and that's what interacts with the other systems. Okay, any question here? Okay, then let's come back to forward converter. So we understand we need forward converter. Of course, this is just one reason why you don't use buck boost, right? In addition, you don't use buck boost because your efficiency would be poor as compared to buck. Not giving you proof now, but right, and you're generally that's the reason there's something called as forward, which is a buck derived topology instead of a buck boost derived topology, and The circuit we saw, I think, last time, but let me still draw it again. This is N1 is to N2. This is D1, this is D2. This is the input voltage, this is the switch. This is what we call as forward converter. How does it operate? If S is on, let me call this one as V1, this one as V2. If S is on, V1 is equals to Vin, right? And therefore, V2 will be equal to Vin into N2 by N1. In this case, you should also see the dot polarities and you should be careful about it, right? Little bit different the way we have drawn it flyback converter. So if this, of course, if this dot is positive, this dot is also positive. So this is how the voltage polarity comes out. In flyback, we have drawn it other way around, right? If V2 is positive, since V2 is greater than 0, which diode will conduct? D1, D2? D1, D2? D1. Okay? Fine, right? If D1 conducts, if you see the equivalent circuit of the output, it would look something like this. You have a voltage source V2 and then the diode is conducting. If D1 is conducting, D2 is reverse bias because this voltage appears here, and you have an inductor and output capacitor. This is how the circuit would look like. We can write the voltage equation for this one. Let's say this is the reference direction. We can say L dIL by T is equals to V2 minus VO. V2 minus VO, V2 is equals to Vin N2 by N1. So this is Vin N2 by N1 minus VO. Okay, similarly, you can analyze what happens when S is off. When switch S opens up, right? For the time being, let's assume this transformer is an ideal transformer. In reality, it may not be an ideal transformer, but it's an ideal transformer. This guy has opened up. You cannot define V1 from the primary side. Why? Because you would not be able to write KVL. So you are not sure what would V1 be. V1 could be anything, right? So if you want to define V1, it can only be defined from the right hand side, right? Now if you see in this structure here, D1 and D2, both options exist. Of course, current can flow through here, current can flow through here, right? Because inductor current cannot suddenly become equal to 0. Inductor current was positive, it was rising, slope was positive, so it cannot become equal to 0. So will it take D1, will it take D2? You can do it by elimination as we have been doing. Let's start considering that current flows through D1. If it starts flowing from D1, in that case the current would leave this dot, right? And this is how the current would flow, fair enough. Then current has to enter the dot. If the current enters the dot on the primary, it cannot flow through the switch, right? So D1 cannot conduct. So the only option left is this inductor current will flow through D2. So D2 conducts and VL, which is equals to L dIL by dt, becomes equals to minus of V0. Yep. Why is G1? D1 necessary means D1 is required. Okay. Good question. So his question is, why is D1 required? What if you don't have D1? What if you have just a short circuit at D1? Will anything change if you do that? Will anything change when S is on? No, because S is on, anyways D was supposed to be short circuit. Will anything change if S is off? Will anything change if S is off? Anyone? Okay, how many of you think that we don't require D1? Raise your hand. At least based on the understanding you have now. Of course we require it, I mean otherwise I would not have drawn it. But based on whatever we have learned so far, how many of you think you don't require D1? Raise your hand. Okay. How many of you think D1 is required? If D1 is not there, this is a short circuit, right? So now this current again will try to flow through the winding, but it will not be able to flow through because current cannot enter the dot. So current will mostly be flowing through this diode. Of course, it's flowing through the diode, so it would create a small V2, negative value of V2, minus 0.7 or 1 volt, minus 1 volt. And this will be minus 1 volt, assuming this is like 50 volt, and 50 volt plus 1 volt, 51 volt will appear across the switch, and switch will be open. Right? So it can work. I mean, looking at it, I don't think there is any problem. But anyone else?
If we have a practical transformer, on the left side there will be that magnetizing inductance. So when that will also have some current when S is on. When we turn the switch off, that current would also still try to keep flowing. So that would appear on the V2 side. But if we keep the diode inactive and that noise appears.
Okay. So what he is saying is, look, what we are drawing here is ideal now. Of course, in next step, in reality, you can never have an ideal transformer. So in reality, you would have a magnetizing inductance, and that actually requires D1. And he has given some explanation of it. The last part is not perfectly correct, but your catch is correct that you require it because eventually there is going to be a magnetizing inductance, and you have to, in that case, you need D1, otherwise things will not operate as you want. Anything else you want to add? Anyone else wants to add anything? So when switch is open, the voltage across winding is very small, 1 volt, minus 1 volt to be more precise, right? Why would it become negative? No, but go ahead, what you got it? But why would it become negative? Current would? Yeah, go ahead, current would? Yeah. So something related to magnetizing inductance would happen, right? We'll come to that. So fine, we'll come to that part very soon. But for now, you assume D1 is there. We'll very soon come to talk about magnetizing inductance, and then you would all know that why we require D1. Any other doubt? So far it's clear. This is how the inductor current would look like. This again can operate in CCM, can operate in DCM. In this context, when we say it's operating in DCM, we talk about the inductor current, right? So except the flyback circuit where we talk about the flux in the transformer, everywhere else, the general nomenclature is that we would talk about the inductor current and define CCM, DCM based on that. Of course, it's a nomenclature, right? There is nothing like this is right or this is wrong. But that's how people do it. So if this is in CCM, you can operate in DCM as well, right? The same converter. You see, this is the same, this is the buck converter, and the voltage source is now, instead of V1, Vin, it's N2 by N1 times Vin. You can use the two equations, you can apply volt second balance, and you can find the relationship between the average voltages, average output voltage and average input voltage. What will you guess? Or I mean, what would you get? Any guess? V output is equals to buck converter hai, so duty will definitely be there. Instead of input voltage, now you are applying N2 by N1 times input voltage, so you would get, yeah. But you can find out, you can use the two equations, you can apply volt second balance, you can cross check if you get that answer or not. Okay. So although this is a buck derived topology, but you can use it to give, a higher output voltage as compared to the input voltage. You can choose the turns ratio N2 by N1 to be such that you get gain, you don't get attenuation, right? You get gain of 10, 20, whatever you want, right? You can get an attenuation also of 10 and 20. Although it's buck derived, does not mean that the output voltage will always be less than the input voltage, right? Because here the gain is coming because of two factors. Because of duty cycle there is an attenuation, and because of turns ratio there is a gain. So you can adjust the two things, right? VO can be greater than, equal to, less than Vin. Any doubt so far? No doubt. Then let's look at the reason for having the diode. Okay, if I draw V1 voltage in this circuit, right, when switch is on it's positive, constant. When switch is off it is almost 0 because D2 is conducting, the D1 is not conducting, so there is no current here, there is no current here, so V1 would be almost 0. So this is how V1 voltage would look like. Is that fine? This is how the voltage across transformer would look like. Anything wrong? Looking at V1, do you feel anything is wrong? What is the average voltage across the transformer winding in this case? It's positive, right? If you apply a transformer with a DC voltage, what will happen? If you apply a transformer with a DC voltage, what will happen? No, its flux will just keep on increasing, right? And it will start drawing more and more current. You will go towards saturation region, but your flux is increasing, so your current will increase exponentially faster, right? And the whole thing will just blow off, right? So this cannot work in practical situation. A transformer, you can never apply DC voltage. You can go back and you can check the voltage that we applied in case of a flyback across the transformer. It was not DC, it was actually AC, such that the average value was 0. It was positive for some time, negative for some time. When the switch was on, it was positive. When switch was off, the voltage coming because of the reflection, the V1 became negative, right? Which was fine because the average voltage has to be 0 across transformer, right? Now in this, therefore, if you actually want to implement this circuit will never work with a actual transformer, right? In circuit simulation it may work because it's some ideal transformer. In reality this circuit would never work. Is that okay? We have to figure out a way of making this voltage have some negative component so that the average is 0. In this case the V1 voltage is plus and 0. Average is positive, right? Average is not 0. So if you apply a transformer a positive average voltage, the transformer flux will just keep on rising, right? And current will also keep on rising exponentially because you remember the BH curve, na? Flux versus current, it's like this. So if this is rising linearly, if the constant DC voltage, this will rise exponentially, and sooner not later your circuit will just reach its capacity. Huge current flowing here, the switch may burn, the source may not be able to supply, something or the other will go wrong. So this circuit cannot work in practical conditions, right? Is that okay? Any doubt so far? Bol? Any suggestion? Okay, so what do? in reality, instead of this circuit, what we use is one more winding, right, on the same core. So now there is 3 windings, and the third winding, that's how we put the third winding. On the same core, right? So you have this core, right? Let's say you have this core. So earlier you had one winding, and above that you had another winding. Now you have a third winding on it. So basically you have 3 windings on the core. Okay, how it helps is as follows. Okay, first of all, let me come back here. So one way to argue is this way, that look, V1 cannot be always positive. The other way to argue is, in reality you will have a magnetizing inductance, right? And when the switch is on, this magnetizing inductance will see a positive voltage. When switch is off, this current which is flowing like this would require a path to continue to flow. Right, so if it cannot flow through the switch, if it leaves the dot, it cannot enter the dot from here because there is a diode also. So that is also one way you see this circuit cannot really operate with a practical transformer. So one way or the other, these are all interlinked because we understand that the flux and the LM is interlinked. So they are interlinking arguments, but you can see whichever angle you think is more convincing to you. Once you have this third winding, then this is what happens. So this is the inductor IL. I am also drawing the current of ILM, which is the magnetizing inductance, this one here, LM, right? So these are 2 separate inductors. Now I will also draw LM. When S is on, ILM will increase, right? If S is off and if you don't have this winding, then this will just suddenly fall to 0. But if you have this winding, now what can happen is the current can flow in this loop, current can leave the dot here, current can enter this dot here, and this excess energy or the excess current can flow in this loop. It will provide a negative voltage and current will fall, because now if this current is flowing through here, this dot will be at negative potential, right? Because this positive will connect here, negative will connect here. So dot is at negative potential. So here also dot will be at negative potential. That means you will have a negative voltage applied across the inductor. That means inductor current will start falling. So your current will fall and come to 0 at some point of time. Right? So now in this case what happens is V1 is positive when the switch is on. When the switch is off, the voltage across V1 is reflected voltage from here, which is negative. So instead of 0 you have negative voltage, something like this, right? And this explains why you need D1, because now this voltage is negative. So you have to make sure that D1 is there to block this voltage appearing across the other rest of the circuit. So that D1 gets explained through this negative voltage. Also what explains this is that now there is a path for this current to flow through, it's not getting disconnected. The average voltage across transformer now can be 0. In this figure you don't think it is 0, but you can always make sure that define the turns ratio such that this negative part is more peakier or something. So you have a way of making the average voltage also equals to 0. So in reality you have this tertiary winding when you use a forward converter. But most of the books will not actually talk about it, not talk about this, will show you the first circuit. But we had to briefly talk about it because somebody asked the question why you need D1. But otherwise I didn't intend to talk about the tertiary winding at least in this course. So even if you could not really grasp 100% of the tertiary winding part, that's okay. I'll not. How will it enter the? No, it won't enter. So this current will flow like this. So current is leaving the dot. So somewhere current should enter the dot. So it cannot enter here. So it would enter the dot here. And this entering the dot means this loop will turn on. And that defines the voltage across this. reflected voltage you can see across this, you will find a negative value. Any question? So I would say that, you can go back, you can look at this tertiary winding, try to explain it. Maybe we can add a question in the assignment. Very simple, straightforward, that considering the tertiary winding and the magnetizing inductance, just ask them to draw some waveforms, ask them to write some basic equations and so on, right? We can add a question on that. But don't worry, I don't really expect you to know this information, but of course this doesn't really, it's too difficult also, it's just a circuit analysis part. Okay, anyone wants me to explain this again? Which part? Iron waveform, okay. Is this okay? Why is it negative? Okay. Unfortunately, this figure could have been bigger, would have helped, but let me still work with this smaller figure and a yellow chalk. Okay, now when switch is open, S is off, right? This current flows through here, so current leaves the dot and therefore current enters the dot. And if this is V1, this is V2, and let me call this as V3, right? And therefore V3 is equals to V1 into N1 by N3, where N3 is the turns of the tertiary winding, right? This is okay. So if current enters the dot, I can write Kirchhoff's voltage law here, and I would see that V3 plus Vin is equals to 0. That means V3 is nothing but equals to minus Vin. And therefore, V1 is nothing but equals to minus times N1, sorry, this I have done wrong, V3 is equals to V1 times N3 by N1, right. So, V1 is equals to N1 by N3 times Vin. So, you get a negative voltage V1, right. This negative voltage gets applied across the inductor. So, V equals to L di by dt. So, current will fall and it will come to 0 sometime. Now, you have to adjust the turns ratio and everything so that you get current becomes 0 before the start of the next cycle, right. So, that you can adjust by how many turns you have to keep. You can keep large N3, then the reflected voltage would be very, very small. If you kept smaller N3, then the reflected voltage on V1 would be very large. Suddenly it will bring it down to 0, right. And now if V1 is negative, V2 is also negative, right. So if you don't have this diode, this will become like a dead short circuit, right. So if you have this diode will block from creating this dead short circuit, right, because now your V1 is, V2 is negative. Is that okay? So you require D1 as well. Is this clear? Not clear? Yeah, it's able to force the current into current. Yeah, so this magnetizing current is flowing through this winding. I mean, of course, in reality, there is no ILM separately there, no transformer separately there, everything is integrated, right? But for our analysis, this is how we visualize it, that for this current to flow, this is how it leaves, this is how it enters. In reality, there are only 3 windings, there is no 4th inductor anywhere in this space, right?
For that part where we are saying that we should not have a DC voltage, even if there is small DC voltage and we operate for a long time, then we can get another design constraint, like that the average voltage across the transformer should be 0.
Must be, all the time.
So here, doing that, would that give us another equation, or would that be just understand the voltage?
Okay, so now this is what I think you are asking. So what he is saying is that fine, we have figured out a way of putting one more winding which will force a negative voltage, correct? But and I also said, so he is saying that, sir, you have said that you can choose a turns ratio N1, N3 accordingly, so that you have sufficient amount of negative voltage, right? But I think what he is trying to ask is, how are you so confident that you would use the specifically same number of N1, same number of N3, precisely calculated for a Vin, so that you get a precisely 0 DC voltage if you average this out? Is that the question? That's the question, no? You get the point. So I am saying, fine, you can, positive voltage Vin will apply, negative voltage, this magnitude is Vin, right? How much is this magnitude? minus magnitude is, yeah, so the total is minus V in into N1 by N3, right? So I can choose let's say N3 to be smaller so that this peak is more, so that the duration required is small to average it out. The duration gets automatically decided by the current slope. So when the average current, the current again becomes equal to 0, this tertiary winding will stop conducting. So the duration adjusts so that the average voltage across transformer is 0. Is that okay? So even if you choose N3, let's say you have taken N3 equal to 10. If you make 9, it's not that now DC voltage will start appearing. This duration will adjust so that average voltage is still equal to 0. Same thing as we were doing in buck converter, right? If you change duty cycle or if you change the input voltage, not that the average will no longer be equal to 0. The circuit rest of the parameters will adjust, right, to make sure that this is equal to 0. Because I don't have the waveforms here, but you go back and look at the waveform. When the primary was conducting, it was positive. When the primary was not conducting, automatically because secondary was conducting, there was a negative voltage getting applied, right? So you had a positive and negative automatically there. So you didn't require it. Any other question? Okay. So with that, I think most likely we would not talk about more DC-DC converters. So we can keep talking about DC-DC converters. There are so many of them, but I think this is where we have to take a stop, otherwise we won't be able to cover rest of the content. What I want to do is now I want to start talking about inverters, right? Power electronics means converting one voltage into another voltage, right? So we have seen how to convert one DC value into another DC value. Now we'll talk about how to convert a DC value into an AC value, right, using an inverter. So some few next lectures we are going to talk about DC to AC. Before we do that, let's a quick revision of Fourier series we'll do before we jump into inverters. You all know what is a Fourier series, right? You all know what is a Fourier series? Why is everyone smiling? You have read in some part of some course, right? Which course? Oh, you know already. Okay. So fine, let's just quickly write it down just to use the variables that we would like to use in this course. So there may be slight variation, name variables different. Udhar X bola hoga, here I'll call maybe Y or something like that, right? So let's just write it down. So first of all, let's see what it means, right, before we write the expression. So if you have a source like square wave, AC source, right, that means it's repeatedly square wave AC source. It's periodic over a period of T, capital T, right. This can be visualized. So if you have this source, right, a square wave source, it can be visualized as a combination of series connected multiple sources of different waveforms or all sinusoidal, right? All sinusoidals of different frequency and magnitude, and they all collectively add. And they give rise to this square wave, right? That's what we mean by Fourier series, right? So if you have a square wave, you can have a triangle wave as well, but I'm just taking an example of a square wave. So if you have a square wave, you can imagine square wave as a combination of multiple sinusoidal or cosine sources of different frequencies, right? That's what is the meaning of Fourier series. In this case, it becomes quite obvious that if you have a sine voltage of the same frequency as square voltage, this is how it looks like. If you have another sine voltage of three times the frequency. This is how it looks like. If you add the two guys together, what you get is something like this. Correct? This looks pretty close to square wave, still not exactly square wave. So you add another frequency term and you keep adding, and so as it will keep looking like a square wave. So if I say this is a square wave of frequency omega naught, where omega naught I will call it as a fundamental frequency. Then I can say that this is made up of multiple components, which includes component of frequency omega naught, which was the main sine wave, another component of frequency 3 times omega naught, which was the another sine wave which I have drawn, and in future you can keep adding more frequency components as well, right, to make it closer and closer to the sine wave. Right, this you all know. I think I am just revising what you already know, more in context of power. So fundamental frequency, third harmonic 3 times, fifth harmonic 5 times, right? Let's just write down the formulae also, and somebody has to help me with that. So if I say, if my this waveform is, let's say V voltage as a function of omega t, right? When you have read it in terms of signals and systems or in mathematics, this was just some f of x, right? This waveform. Now it's not f of x, it's precise. So either we are going to talk about voltage waveform or we have to talk about current waveform. So it would either be V or it would either be I. So it could be V or it could be I. And again x, the variable x which was there, now it's our x-axis is not, we call it omega into t, right? Omega into t. So therefore it would be either I of omega into t or V of omega into t, right? One of these terms. So if I have to write for V, I can write, so V of omega t is equals to half of A naught plus sigma of n going from 1 to infinity A n into cos of omega n t plus sigma n going from 1 to infinity Bn sine of omega naught n into t. Okay, so this means that this waveform we can express it as a combination of a DC source plus an AC source of fundamental frequency plus an AC source of second harmonic plus an AC source of third harmonic, fourth harmonic, fifth harmonic. So all the harmonic coefficients, of course some of them may come out to be 0 when you evaluate them. And An, how do you evaluate? An is given by, anyone recalls it, what is An equals to? What was An given by? Okay, here we will talk about omega t, so we will talk about angle, maybe make it simpler, right, about pi, minus pi to pi, V of omega t goes from, omega t is nothing but theta, right, which goes from pi to minus pi. So V of omega t, which I can represent as theta into cos of n times omega t and theta into dt. So d theta will be equals to d of t into omega. So I can write dt is equals to d theta by omega. Sorry, one second, there's something wrong. D theta, yeah. Correct. Similarly, you can write b of n is equals to 1 upon pi integral going from minus pi to plus pi v of theta into sine of n theta into d theta, and you can write a naught is equals to 1 upon pi integral minus pi to pi v of theta into d theta. So just note these things down, try to remember it. If you don't remember it, no problem. If I have to ask you to solve it, I'll give you the expression. But only thing what you should know is how to apply it, how to solve it and so on. That I think you should just do it once or twice. But let's, once you write it down, we'll just try to have a look at it for a little better understanding. The first component, right, 1 by 2 of a naught is nothing but 1 upon 2 pi integral of minus pi to pi v theta d theta, right, which is nothing but the average value of v. So the first component is nothing but the average value of this. So in our case, if our sources are sinusoidal, even if it's square wave, there is no average value, then this first term might come out to be 0. So if there is no DC, this will come out to be 0, right? If there is a DC component, this will come out to be non-zero. Rest of the expressions you can solve. So for example, you can start with the square wave, try to find out omega naught, 3 omega naught, 5 omega naught, 2 omega naught. You would find that the 2 omega naught value and the 4 and so on would come out to be 0. That means there is no even harmonics, there is only odd harmonics there, right? You want one more too? No, half is only for a naught. No? Anyone else remembers the formula? I think this is okay. Anyways, I'll check it. If it's not correct, I'll let you know. I think it should be fine.
The end expression is 1 by 2 pi about to be we also write 1 by t integral of minus t by 2.
Let's check the formula. Can some of you Google and quickly check the formula? It's fine. That's the reason we are writing it down again, because I know there are different coefficients, there are different limits. The minus infinity plus infinity you are talking about is the Fourier transform, not talking about Fourier series. Fourier series we only talk about periodic signals, so we only integrate from either 0 to t or minus t by 2 to plus t by 2 or 0 to 2 pi, right? Oh, acha, this way. Oh, you mean n equal to minus infinity? Okay, fine. Sure. Fair enough. So this represents the DC component. The first term represents the DC component. So if there are no DC components, this term will be equal to 0. In this case, if you see, I have not added any even harmonic, because this waveform we call it as a half wave symmetric. So what is half wave symmetric? Half wave symmetric means f of omega t or voltage of omega t is equals to minus of f of minus omega t, right? This is what we call it as a half wave symmetric. What it means is if this is the axis, right, this point and this point magnitude is same and they are just negative of each other. This point magnitude is same, they are negative of each other, right? So we call it as a half wave symmetry, right? This I am sure you would have studied, half wave symmetry. So if you have half wave symmetry, you can substitute here v of omega t is equals to minus of v of minus omega t. You can simplify this integral for n equals to 2, and there is a sine, there is a cos. You will find that it will come out to be 0. That means there is no second harmonic here, no fourth harmonic here. There is only third harmonic and fifth harmonic, right? You can go back and you can solve it. It would not be very difficult. Just substitute n equals to 2 and try to find that if you get an value, what is the an value, what is a2 value, you try to find what is b2 value, And you would realize that these guys comes out to be equal to 0 if you have half wave symmetry. That means there is no even harmonic, no second, no fourth, no sixth and so on. Is that okay? We'll talk more about why harmonics, what is the impact of it later on in this course when we talk about power quality, right? So power quality means the source we are getting is not sinusoid, it has some harmonics. So all those things we talk about when we talk more about power quality, but so far this is how we define the different harmonic components, right? Just a little bit more about harmonics, right? So if you have this waveform, it's composed of, as we saw, sinusoidals of different frequencies, right? The RMS value of this, right, is related to the RMS value of the individual components as Vrms squared is equals to fundamental component RMS squared plus the second harmonic component. There is no second harmonic here, but as a definition this is how the total looks like, plus the third harmonic RMS squared, plus of course we should not miss out the DC component RMS squared, right, and you keep adding this thing. So the total RMS is square of the total RMS is square times addition of the squares addition of all the individual harmonic component. Again, this is something which you can easily prove using the Fourier series term. Have you done that? Have you seen this before? This first time you are seeing it? You have done it? Oh, VDC is the DC component, 1 is the fundamental component. VDC is 1 upon 2 A naught is the DC component. This is the fundamental component, this is the second harmonic component, this is the third harmonic component and so on, right? So if you square each of them, you add, you get the total RMS. We also define total harmonic distortion, which is defined as, total harmonic distortion is defined as, total harmonic distortion, this I have taught you, na? No? Okay. So we want sine wave supply, right? Sometimes you don't get sine wave supply, we are upset. So question is, how do we define how much upset you are? You define, you can say, oh, this has a fundamental component, sine wave, plus it has a 50 RMS value of the second harmonic. But you know, this may not be able to give you a uniform picture. Some other voltage may have a 60 RMS value of third harmonic. So what we define total harmonic distortion, which means how deviated the supply is from the pure sinusoidal voltage, and we define it like root of V1 RMS squared plus V2 RMS squared and so on divided by V1 RMS squared, right? So this in a way gives us the percentage value or the ratio of how many harmonics you have with respect to the fundamental component. No, so there is no V1 here. Huh? So sorry, there is no V1 here. It only starts with V2 and so on. So ideally, total harmonic distortion should be 0. Ideally, total harmonic distortion should be equal to 0. If you take a pure sine wave, you will get THD equals to 0. So for a pure sine, total harmonic distortion, total you can define it as ratio, you can define it as percentage, up to you. What it tells is, okay, how much of third you have, how much of fifth you have, right? Because all of those terms get added in the numerator. So this defines in a way the purity of the sine wave, or how close a waveform is to the sine wave. Yeah, THD can never be greater than 1. THD can be greater than 1, why not? You may have this thing very, very small and the others may start dominating. You can have THD more than 1, no problem. Because numerator there is no V1, na? Numerator there is no V1, V2, V3, V4, those can be higher. This could be small. You can have a fundamental square a small sign and the harmonics is huge. Theoretically it's possible. When you, I'll give you an example where you can actually see these values, right? So if you have, all of you know a UPS, right? UPS, you know, all of you know what is a UPS? UPS, you know UPS? How many of you know UPS? Raise your hand. Uninterrupted power supply. So it's like a box where you give a supply. What is the other UPS? That's okay, that's pretty close. I thought, thank God you're not talking about the UPS courier service, right? Which is, I think, stands for US Post or something like that. So UPS is like a black box, right? Which has an input supply and which gives output, which you use it in your office or home, so that if the input also gets disconnected for whatever reason, through a battery backup, you keep getting the output, right? It's like an inverter, right? So if you search for any UPS system, then they would define the current that they are drawing from the grid, right? So if this is your UPS and this is your grid and this is your load. So the current they are drawing from the grid, they would define what is the total harmonic distortion of the current that they would draw from the grid, right? And those values would be typically 5%, 10%, 15%, 20%. That means what they are claiming is that they will put it in their spec sheet. What they are claiming is, look, our UPS is so nice that it draws a current from the grid which is almost sinusoidal, as compared to, let's say, a competitor who draws a current which is really bad, but I can draw and show you how bad it looks, but how do you quantify it is using total harmonic distortion, right? So you use THD to, in a way, quantify how good sine wave it is. And in our power electronics and power system, sine wave has a lot of value, right? Because the current you are drawing from the grid, you want to be equal to sine wave. You don't want harmonic current to be drawn and so on. So this is just an example. If you look at maybe these LED lights, they don't mention the THD, but they do mention power factor, which includes THD, and I will come to that a little bit later. Let me think of another example where you can explicitly find the THD. The solar inverters, if you see the solar inverters, they inject a current into the grid, right? So the current they inject in the grid is again pure sinusoidal, and they define the pureness of that sinusoid using total harmonic distortion. Is that okay? So this is a very useful term, we will keep using it. Second square RMS, third square RMS, fourth square RMS divided by the fundamental. What is V2 RMS in terms of these coefficients, A n, B n, whatever, all of these things, right? What is V2 RMS in terms of these coefficients? In these coefficients, what is V2 RMS? So this is the main equation, right? And these are how you derive the expression. So just look at the main equation, and now which parameters will form V2 RMS from here? So if you see, V2 means second harmonic, so n equals to 2, right? So this term is anyways DC, n equals to 2 means you will have an A2 cos of 2 omega naught t, you will have plus B2 sine of 2 omega naught t. This is the only second harmonic component, right? Can you find the RMS of this? A2 cos of 2 omega t plus B2 sine of 2 omega t, what will be the RMS value? You do root, mean, square, A square plus B square plus 2AB, right? A square cos square omega t plus B square sine square something plus 2 times A into B into something. You try to solve it. What will you get? What will you get? Yeah? A2 square plus B2 square by? No, I don't think so. By 2 should not come. I think it should just be A2 square plus B2 square. But you can try it. Assignment mein de de. Let them prove. Let them, write with their pen, pencil. So your V2 square is nothing but A2 square plus B2 square. Oh, yeah, you are right. Correct. So A2 by root 2. Right, no, you are correct. Yes, absolutely. Absolutely. So A2 is the peak value, so A2 by root 2 is the RMS of that cosine component, B2 by root 2 is the RMS of the sine component. The total RMS is under root of RMS of sine square to RMS of cosine square. So this is the total second harmonic RMS, right? So now if I give you a square wave, you should be able to find the coefficients for the square wave using these formulas. You should be able to use these coefficients to find the harmonic RMS values. You should be able to use the harmonic RMS value to find the total harmonic distortion. And that way you should be able to quantify the waveform I give you. If I give you a square wave, sine wave, some other random waveform, you should be able to tell me what is the total harmonic distortion in that waveform. Is that okay? Good, that is a question I can then ask you. I think this is something which we can ask them in the assignment. Yeah. I think what he's saying is that, look, if you use these two relationship, right, you can substitute all of these things into this formula. So this numerator will be total RMS square minus V1 RMS square, right? You can find the total RMS square using the RMS process that we do. V1 RMS square only for the fundamental, and then you can get the THD much faster. Yeah, this waveform doesn't have any DC in general. So anyways, this would be 0. If anyways this would be 0. If it had DC, yes, you have to incorporate the DC component. This is what you mean, right? Yeah, you can do that. Okay, so any further question on Fourier series? Half-wave symmetry also I want you guys to prove. I think you have already done it as a part of some other course, but I want you to prove that if f of omega t or f of theta is minus of f of minus theta, you can just substitute that in these expressions and try to find the coefficients A2 and B2 and prove it that they come out to be equal to 0. Why is it so important that 0? Because usually when we draw the waveforms, we draw it half-wave symmetric, right? We draw sine wave is of course half-wave symmetric. F of theta is equals to minus of f of minus theta. We draw a square wave that is half-wave symmetric. Most of the time the voltages that would be there in the grid would be almost half-wave symmetric, and therefore predominantly you would have odd harmonics in the grid. The even harmonics would be very, very small, right? You remember the current that, you know the diode rectifier, right? Full bridge diode rectifier. What is the current that you draw from a full bridge diode rectifier? Is it half-wave symmetric? Full bridge diode rectifier. क्या लगाना है? कैपेसिटर, इंडक्टर. You want to connect capacitor, inductor, resistance, which one? कुछ भी बोल दो यार, मतलब we'll just use that as an example. Whichever you think is simplest. Resistor, okay, चलो. Resistor में sinusoidal भी आ जाएगा ना. Let's make it little bit complicated, ना? Capacitor and a resistor, because most of the power supplies would have this kind of thing. So in this case, we understand if the input voltage is like this, right? The output voltage would be like this, right? Keep going that, and the current that you are drawing will be after it settles down. The current will be, there will be negative peak here, there will be some positive peak here, and so on. So if you see the current here, it would be half-wave symmetric. That means whatever happens in the positive cycle, the same thing happens in the negative cycle with a negative magnitude after pi, right? So if you shift it and you invert it, you will get the same waveform. That is what it means, right? Half-wave symmetric. Half-wave symmetric means f of theta is equals to minus of f of minus theta. That means if you shift it by t by 2 and you invert it, you will get the same waveform. So the current that you draw here is half-wave symmetric, right? And that is the reason I am saying that most of the currents and voltages in the power network would be half-wave symmetric. Most, not always. Can you give me one example where it would not be half-wave symmetric? Yeah, if you have a half-bridge rectifier. The voltage is half wave symmetric, right? What about the current? Current is not half wave symmetric. If you shift it by pi and if you invert it, you won't get the same answer. You won't get the same waveform, right? So only this half wave rectifiers don't have symmetric, half wave symmetric currents. Other than that, most of the rectifiers which you use in the network have that, and therefore most of the current that is there in the grid is half wave symmetric, and therefore we have rarely even harmonics. We always have odd harmonics in the grid, right? Is that okay? In fact, you will be surprised that even your mobile phone chargers, right, doesn't have this. It has this. And so you can imagine this is okay for theoretical, but in real life this would be used, not even like 20 watt of charger, 30 watt charger doesn't even use it. So there's very rare finding of such waveforms which is not half wave symmetric. Okay, any question? So let's stop for today at this point.